Thank you. Thank you. I'm Nimrod. I'm here from the CBU, and today I'm going to cover network analysis with behavioral data. I'm going to go over some basic principles, show some network algorithms, and give some code example in R, talk about the limitations of network analysis, and conclude with some centrality measures. Some of this, for people who already heard talks about network, is going to be repetitive. I apologize in advance, but you're stuck here, so deal with that. So what are networks? When we talk about networks, we would usually refer to some set of multivariate system that has some dynamic of the different actors within that system. So underlying underneath this graph here that demonstrates just a random example of co-authors on papers, there is an adjacency matrix that shows the different connections between the people here, whether they are connected, meaning they wrote a paper together, and then they get a value of 1, or they didn't write a paper together, and then they get a value of 0. And usually, in the networks, we'll have two important elements, which are the nodes, or vertices, representing some sort of entity. In this case, these are the co-authors, and the edges that connect them. So, for example, here, we can see that Diana and Queen wrote a paper together, therefore they are connected by an edge, but Diana and Liam didn't write a paper together, so they are not connected. Maybe next year they will write a paper together, and then the network will change. As we mentioned, it is dynamic. But usually when we deal with behavioral data, we would not be interested solely on whether edges are connected or not, but instead we'll talk about conditional dependencies, meaning that we would like to see the connection between the nodes while accounting for all other elements that we also measured. Meaning that if we compare it, for example, to Pearson correlations, the picture that you see here on the left, which now represents not people, but in this example, symptoms of depression. So we can see that all of the elements are highly connected between them. So it doesn't give us a lot of unique information. But we might be more interested in seeing what, after you account for all the elements, is still uniquely associated and affects one another in a stronger way. And this is the network that you see on the right, where you can see that the connections are much weaker than the one on the left, but are more informative for us. So that's what we mean when we talk about the conditional dependencies. And we'd usually get that through a combination of partial correlations with some sort of regularization, meaning that we are giving some penalty for especially small effects. So if an effect is very small, I would turn it to 0, and the decision of how small is very small is up to me and controlled in my network analysis. And because this is usually a very complicated structure that is sometimes hard to follow, especially if I have a lot of nodes, I would usually also calculate some features of the network that can be either global features, features that refer to the network as a whole, or local features that refer to more specific elements within the node. So example of global features, this is not an exhaustive list, but it can be the network density, meaning how much the network is either dense or sparse, that we get from looking at the ratio of actual edges to all possible edges. The average path length, sort of a measure of how fast information travels within the network, what is the shortest way to get from each point of the network to the other, the clustering coefficient, the probability of neighbors of a specific node to be connected themselves. And we have many other global features that we would be interested in. And the local features, the most important of them, or the most popular of them, are usually centrality measures that I will touch on later in this talk. And when we are trying to observe some behavioral phenomenon, so networks can also give us a new way to conceptualize the phenomenon. And what do I mean by that? So we mentioned depression, and we can ask ourselves, what is depression? And one way to answer that would be, depression is some sort of underlying factor that has symptoms. So a person can either have or don't have depression. And if they have depression, we would expect to see low mood, low energy, slowed movement, etc. But another approach would be to say all of these symptoms are not the outcome of this underlying factor named depression. Rather, they form some sort of structure, some sort of dynamic interaction between them. And when organized in a specific way, the outcome of that would be that a person has depression. And depression is just one example, but you can think of anything that you're interested in, and you might be able to conceptualize it through a network, which gives you a new way to think about the phenomena that you're interested in. Now, there are many types of networks. We can have, for example, networks that are undirected and unweighted. So I gave just random example of a very simple network where you can take 3 random people, call them Elon, Donald, and Stormy, and we can ask ourselves who knows who. So this network that is unweighted, undirected, and completely fictional tells us that Elon knows Donald, and Donald knows Stormy. And this is all of the information that I have. But we can also add more attributes to discover more information. For example, we can ask ourselves, how well do they know each other? And now use a weighted network. So the weighted network gives us information also about the strength of how well they know each other. So the thicker the edge is, the better they know each other. We can see that Elon knows Donald pretty well, and vice versa, and Donald and Stormy are not so much. We can also have a network that is directed and ask a question like who saw who on television, and it gives us information also about the directionality of the edges. So we can see that Donald saw Stormy, and Stormy saw Donald, and Donald saw Elon, and Elon saw Donald, and Donald saw himself. So that's another information that we can get from the network. And now, because I really want to be canceled, we can also ask ourselves who paid who, and use a network that is both directed and weighted to answer that. So we can see that Elon not only just paid Donald, but paid him quite a lot, and Donald paid Stormy, but not so much. So maybe Donald has some extra money and can go to McDonald's. Now, different samples would require different networks if I want to analyze them properly. So I can think of if I have cross-sectional data. That is where I have only one data point, but a lot of participants. And for that, there are a lot of network algorithms, but the most popular of them would be probably the graphical Gaussian model, or GGM, or the Ising model, in case that I have binary data, and we'll touch on them in a minute. There's also an algorithm named directed acyclic graphs, DAG. I won't talk about it today, but I thought it's worth mentioning because it's pretty useful, though it has a lot of problems and a lot of assumptions that are quite unrealistic. We can think of panel data. That is where I have multiple participants and more than one time points. So for example, if I have a longitudinal study with 3 time points, I can use different algorithms to also show temporal effects, meaning how each component of the network affects other components in the next time point. So time point 1 affects time point 2, etc. And for that, I would usually use an algorithm named vector autoregression, or VAR. And I can also have a time series. So in a case where, for example, I have only one participant, but that participant have multiple time points, like the case that I'm wearing a tracker and I'm interested in some physiological data and how the different elements interact. So I can also use VAR in this case, but this time it will be an idiographic VAR, meaning VAR within a single person's level. And of course, I can have multiple people with time series, and for that I can use hierarchical VAR that also gives me some additional information on top of what the idiographic VAR gives me. So I'll wait for people to take a photo, and I can also send you the slides later if you're interested. So let's talk a bit about those algorithms. I want to present them just very briefly, just give you an example, and anyone who's interested is welcome to talk to me later. Starting with GGMs, this is usually the algorithm that we would use for cross-sectional data if we want to see between-person effects. And it works with normally distributed data coming from continuous variables. Usually, GGM would use G-lasso for regularization to shrink the network and make it sparser. And I can determine how sparse I want my network to be. And the network will be undirected and weighted. And there are multiple R packages for that. There's also multiple Python packages, but I'm going to show an example with R. So here, for example, I'm using a package named bootnet that is very useful. because it calls a lot of other packages and uses them with bootstrapping, so I like it. And you can see that I asked it to do GGM using this command of ebic glasso, which also adds extended Bayesian criteria to it. And the tuning variable here is the regularization parameter that I would use. And the higher this parameter would be, the sparser my network will be. And I'll have fewer edges, but I'll have more certainty in the edges that they represent actual connections. The outcome of this command would be this matrix that is called a precision matrix, kind of similar to the adjacency matrix, but deals with conditional dependencies. And I can then use a package named QGraph in order to visualize my data and show the network, which, as you can see, is undirected and weighted. So I don't have any information of what affects what, but I do have information of how strongly different elements, different nodes are associated here. And I mentioned the regularization parameter, and this is an example of how using a different package, this time glasso, that uses a different tuning parameter. This time it's not gamma, it's rho, just slightly different calculation. I can get, with the same data, networks that are different from each other. And you can see that as I increase my parameter from 0.1 to 0.25 to 0.50, the higher the parameter is, the more regularized the network is, and the sparser it is. And as a rule of thumb, I would choose lower parameters if I'm more interested in sensitivity and in discovery, or if I have fewer data or the connections are not so strong. And if I want a network that is more specific, or I have a lot of data, or I want to be more confirmatory, I would use higher parameters to regularize my network. The icing model, I'm just going to cover it in 30 seconds. Its application is quite similar to GGM, only with binary data. It's a network. It's an algorithm that is lent from magnetism to calculate the probabilities of a phenomenon to either be or not be, to be in one of two binary positions. And it also has a lot of different R packages. Here, I calculated it, again, using bootnet, just changing the algorithm and remaining with the same tuning parameter. And you can see that I'm getting a network that, similarly to GGM, is undirected and weighted. But you can see that with the same parameter, this network is much sparser. It did not reveal as many edges as the GGM, which makes sense as I shifted with the same data from continuous variables to binary ones. So I lost some variance in the process. Lastly, I want to mention var. So as we said, var would usually use when we have longitudinal data of continuous variables. And var actually produces two networks. So it starts by calculating a temporal networks, showing the effects of elements in the previous time window on the current time window. So I'm looking one time point backwards to see its effects on the present moment. And then using the residuals, the variance that is not explained by the temporal effects, I'm calculating the contemporaneous network that shows me the network or the effects that occur within the same time window. And sometimes the same nodes can be connected in opposite directions in temporal or contemporaneous matter. So you would see it in a second. So var, I'll just give an explanation before addressing the other points here. So I would start with some longitudinal data. In this case, what I have here is a time series. So you can see that all of my data is time-stamped. This is all data coming from a single participant who answered questionnaires multiple times a day over a period of a few weeks. And very importantly, I have these two variables here notifying me of the day that each observation was recorded at, and the beep, which means the time within the day. And that's important for me because I will use it later in my var algorithm to alert it to the order of the observations. And that's important for the temporal effects. So the network looks like this. This is the output. I would have my temporal network showing the effects of, in this case, now we shifted from depression symptoms to PTSD symptoms. It's a very cheerful talk. So I can see that, for example, negative appraisals affect negatively mental well-being in the next time window. Meaning if a person is experiencing negative appraisals in the next time window, I would expect them to have lower mental well-being. So when the line is red and dotted, that means a negative effect. You can also see, as we said, some opposite conflicting effects, such as here that triggers predicts lower negative appraisals in the next time window, but within the same time window in the contemporaneous network, the effect is actually positive. So they are positively correlated. It actually makes sense. You can think, for example, of the connection between exercising and energy levels. So contemporaneously, when I exercise, I'm very energetic. But then if you'll ask me 3 hours from now, I'll probably be more tired and less energetic. So it makes sense to have opposite effects. VAR has a few limitations that I want to touch on very quickly. First of which is the stationarity assumption. VAR assumes that the variables are stationary over time, and in a lot of cases, it's not true to the actual data. Like here, that in this data, we measured PTSD symptoms, and there is symptom reduction over time. So it's problematic for VAR assumptions. One way to address it is to use detrending and regress the effects of time on the different variables. So I'm trying to take out all the variance that is explained by the time that have passed. And then what I get from the residuals is the same variables that are now stationary. So this is one minute. So this is one trick to tackle stationarity. And there are other limitations that I won't touch on today, but you're welcome to talk to me afterwards. In the 40 seconds that's left, I want to touch on centrality measures. This is a local feature trying to summarize for specific nodes how much they are influential in the network, either affected by or affecting on other nodes. 3 very popular centrality measures would be the strength, which is the total sum of edge weights connected to each node, closeness, an estimation of how close nodes are to other nodes in the network, and betweenness, how much nodes are bridging the shortest path between other pairs of nodes. So for example, this here guilt is very high on betweenness for a simple reason, because it connects suicidality with all other nodes in the network. So it will be very high on betweenness, but not so strong because the sum of edge weights is not that high for them. So that's it. There's a short summary here. And again, anyone who's interested in the slides, let me know. I again would recommend you, if you're interested in this, to look for materials by Sasha Epskamp. He's either on YouTube or he has great papers on it. A lot of this talk was influenced by things that I learned from him, so a lot of credit goes to him. I never met him, by the way, so no, just, yeah. And thank you for listening. You're also welcome to email me or to catch me here around CBU. Thank you.